Okay, so hi everyone. Good evening. Welcome back to Plan 258. Uh, the agenda for today, I can discuss about this topic. No? Today we'll discuss about ideal flow network. So discuss about an equivalent, power dynamic, and signature, and then this is kind of summary on how to apply IFN. Yeah? And then if we have time, so we can continue with IFN for prioritization. Otherwise, we can continue next week. So all this topic you can follow in Moodle and Revoledo. Okay. So you can open the slide. I'll share this screen. Let's start with the first topic, which is IFN equivalent. Can you see my screen?
Yes, Doc Kardi, we can see your screen.
Very good, thank you. So in this topic, okay, we'll discuss about what is equivalent IFN. So we discussed IFN last meeting. Okay, so last meeting we discussed about what is IFN and how to compute the IFN, including the network representation. Okay, so today we'll go to the next level. So we talk about special type of equivalent IFN and certain invariants. Okay, and possible application, okay? Especially for transportation. And then we will have lab session. Okay. So this is the basic idea of ideal flow network or IFN. Yeah? So you have what is called capacity matrix here. The square matrix represent your network and the strength. Okay. So and based on that capacity matrix, you can create the proportion to get what is called stochastic matrix. As here represent the stochastic matrix. Yeah. So yeah, this stochastic matrix represent in transport network represent a probability to turn left, right, or go straight. Yeah. So this is in transport network represent the number of lanes. Yeah. Now, based on the stochastic matrix, okay, you can compute what is called the node vector. Yeah? This is basically the Markov equilibrium vector. Okay? Of course, you need to give a certain value, which is the total flow in the network. Kappa. Now, based on this two, okay, now you can compute the IFN, which is the ideal flow matrix here. Now, because you know the congestion, because you know the flow and the capacity, then you can get the congestion. Yeah, G is the congestion level. Yeah, so these are the basic idea of IFN. Okay, regardless your application in different methods, so the flow is something like this. Yeah? Sometimes you don't have the congestion matrix. Okay, you only get until the IFN itself, okay, or until the V here, the node vector, that's okay. Yeah. So today discuss about equivalent IFN. So suppose you have two flow matrix. Yeah? So let's call this F1 and F2. Both have the same stochastic matrix. Okay, remember, it comes from a stochastic matrix and then you can get the flow matrix. Yeah? Now, suppose the same stochastic matrix, now you have two ideal flow matrix. Yeah? Of course, this the two ideal flow matrix, yeah, F1 and F2, must be equivalent because they have the same stochastic matrix. Yeah? So they must be scalable by certain global scaling alpha. Now, because they are equivalent, okay, so there are certain invariants, something does not change. Okay, so based on the tree here, you can see there is something not changed. Yeah, later you will start to come with, for example, the coefficient variation of the flow does not change. Yeah? The entropy does not change. The information does not change. Yeah? Many of the performance, yeah, does not change between the two ideal flow matrix, yeah, F1 and F2. And then because of that, we can also create what is called standard form. Yeah? So for example, if the minimum is 1, so we call it unit minimum. Yeah? Unit maximum is the maximum is 1. If all integer, we call it alternate network. Okay? If the total is 1, we call it basis network, and so on. So let's go to the definition. Yeah? So suppose you have two networks. Yeah, this is like a while ago, F1 and F2. So we have N1 and N2. There are two ideal flow networks. Yeah. So then we say the two IFN are called equivalent if and only if. That means this is only happen if. Yeah. If the corresponding link flow of one network is a multiple of positive global scaling. Yeah. So meaning you can multiply each element here with certain value, say global scaling S here, then you can say that this is actually equivalent. Yeah. So this is by definition. So to prove this, we need to understand the definition of equivalent. Yeah. In mathematics, definition of equivalent means reflective, symmetric, and transitive. That's the properties of equivalent. Yeah. That's the meaning of equivalent. So that's reflective means if the scale is 1, you get exactly the same thing. Yeah. Symmetric means if you have N1 scale to N2, then you can come back to N from N1 to N2, okay, and so on. And then if you have three networks, so N1 is scaled to N2, and then N2 in S scaled to N3, then you can always scale back from N1 to N3. Yeah, these are the proof that global scaling operator is actually equivalence IFN, yeah? Mathematically, as simple as that. Okay, so let's practice first. Okay, assuming you have uniform probability, so the stochastic matrix is given. Yeah? You from A go to B have 50%, and then A go to D also 50%. Yeah, and then from B go to C and D again 50-50, and then C go to A and B 50-50, and D going to C 100% because there is no other link. So can anyone start to compute this IFN manually? So when I do this manually, okay, so I assign any value, for example, 100 here. Okay, and from C to A, I assign 100 because this is 50-50. So then the next steps, I distribute, right, 50 and 50 here from A to B, and A to D become 50. Okay. From here, let's go to the next step here. Now let's focus in node P. Yeah? So in node P, you have going in 50 here, but from C to B, we don't know. Okay. But we will distribute this flow into 2. So in that case, let's put this x. But if we put this x, this will become half of x. So in that case, let's multiply by 2x so that when we distribute, will become x only. That's easier to compute, right? So we assume this is 2x. Okay. So from there, we distribute in node P because enter is 50 and 2x. Then BD become 25 plus x and then 25 plus x. Okay. Can you see this? Okay. And then from BD is 25 plus x and then enter here is 50. So become 75 plus x, right? Going out here is 75 plus x. Okay. And then coming here in node C, you have 25 plus x plus 75 plus x. Okay, so 100 plus x. Oh, 100 plus 2x, right? Which is correct because 100 going back there and then 2x going there. So this is pretty much x already. Yeah. So we just don't know what is x. Yeah. So I assign, okay, in that case, what if I assign x equal 1? What if I assign x equal 2 and so on? Okay. So then the IFN is not unique in that case, isn't it? So what is the correct x? And the correct x must be the one that actually pass through this stochastic matrix. Okay. So if you assign x equal 1, okay, this is no longer the same as the stochastic matrix is not the same as this one. To make it the same, then x must be 50. So here in this example, so I put here x equal 1. Here it becomes 26, 26, which is correct. Okay. But if you look at this, the stochastics is not exactly correct. This is 50-50, correct, 27, 26. Okay. If I put x equal 2, I will get this value. Okay. And if I put x equal 3, I will get this value, and so on. Okay. So if I put x equal 50, okay, I will get this value. Okay. So which one is the equivalent IFN? Yeah. So if we compute using computer, you will get this value. It's not even the same as all of this, right? And actually, this is actually equivalent to this. Yeah, because this one multiplied by 25, you get exactly this one. Yeah. So this is the equivalent IFN. Yeah. And this is not. Yeah, this is not. This is not. Is it clear or not? Any question up to here? So, do you get the idea or you don't?
No question so far, Doc.
Okay, no question so far. Really? Great. So, what's the implication of that uniqueness? Yeah. So, two IFN will share the same stochastic matrix if and only if they are equivalent. Okay. That means when we say if and only if, that is two-way. Yeah. So that means if two ideal flow are equivalent, then they share the same stochastic matrix. And the converse is also true. Yeah. So if the two ideal flow have the same stochastic matrix, they must be equivalent. Okay. So then these are the properties. Yeah. So if you have two IFN is equivalent, they will preserve the stochastic matrix. Okay, because of that, so they will also preserve many invariants. Okay, for example, coefficient of variation of flow, which is standard deviation divided by mean. Okay, this one also invariance. The coefficient of quartile variation of flow, the IQR, and divided by the median. Entropy, for example, or minimum divided by the maximum of flow, and so on. These are also equivalent. Okay, let's see this later, okay, when we practice. So there's now, given the definition of equivalent IFN, now we can define several names. Okay, the name is actually to make us work easier. Okay, so number one is, we call it basis network. What is basis network? If the total flow is one. Okay, and we call it cardinal network. Cardinal mean integer, right? So this is equivalent minimum integer. Okay, again preserving the stochastic matrix. They are equivalent. Okay? And we can name it unit network or a minimum unit network. Okay? This is equivalent IFN with the minimum flow of one. Okay, so maximum unit network. So that means we call it cup network. That is the same as maximum flow of the network is one. Okay, we can also make the mean, the average, the arithmetic mean is equal to one, or the median equal to one, or the standard deviation equal to one, or the interquartile range equal to one. So these are all, when we say equivalent, all of these will have one stochastic matrix. Okay, I give you example so that you can get idea. Okay, so say in this ideal flow matrix, okay, so the total is one, kappa is one. Okay, so and if you look at the values, yeah, we divide into 49 all, right? That means I can simply multiply by 49, okay, all of these values, then I can get integer, right? So when the total flow in the network is one, right? So this value represents the link probability. Okay. Okay. Now, you can also get the next equivalent with this maximum flow in the IFN is one. Okay. How to do that? You divide each link flow with the maximum flow. Okay. And when we say unit network, that means the minimum flow in the IFN is one. So you divide with the minimum and so on. Yeah. So one thing is interesting is called cardinal network, okay, with this equivalent IFN that preserve the stochastic matrix with minimum integer flow. Okay, so how to get that? Okay, first you put all the link flow into fraction. Okay, and then you get the LCM or least common multiple of the denominator. Yeah, and then you multiply with that scaling, and with the LCM. So a while ago here, the denominator is 49, right? All the same. So in that case, multiply by 49, you will get this cardinal network. Of course, now the total flow becomes 49. Okay. Is this clear? So now if we divide, okay, the flow in IFN with coefficient variation of the flow, my question, will the equivalent IFN have the coefficient variation of 1? How about if we divide the flow in IFN with coefficient of quartile variation of flow, which is IQR divided by median? Will the equivalent IFN have coefficient quartile variation of flow of 1? Okay, so the answer is not. Yeah, why not? Yeah, because these are the invariants. Okay, so later we will discuss the invariance section later. Okay, let's get the definition of global scaling. So the value that we put, yeah, multiple from one IFN to the other, the equivalent IFN is called global scaling. Yeah. Why we call it global? Because we need to multiply with all the links flow. Okay. There is another theory of IFN that we can actually multiply in each node with this local scaling, okay, which is out of the scope of this subject actually. Yeah, the mathematics will be too deep. Anyway, so for you, I hope you can start to practice. Okay. Can you find the LCM of the denominator of this IFN? This is already IFN, yeah? So can you get the global scaling? Wow. How do you get that win? 18, we can say.
We can get it, sir, by prime factorization. So 9 is 3 by 3, 18 is 3 by 6, 3 by 3 by 2, then 6 is 2 by 3. So 2 times 3 times 3, that's 18.
Okay, super, right? Okay, you can do prime factorization. Okay, so the LCM is correct, yeah, 18. Okay, so once you have the LCM and this common multiple, yeah, then use that LCM as your global scaling. So you get 18. So multiplying all this link flow with 18, you will get integer. Yeah. So this is cardinal network. Is it clear?
So is that network also the minimum?
Yes, this is the
network
unit
with
minimum. Yeah, the unit minimum.
unit minimum.
Correct. Yeah. So this is also unit minimum. Yeah. So super. Okay. So it can be several, the same network can be unit minimum, can be different type of equivalent. Okay. So now, can you identify the basis network in here? A, B, C, D. Which one is basis network? Basis network means the total flow in the network is 1. Yeah, the kappa is 1. So clear. Yeah. So if you want the total flow in the network 1, that means the flow must be less than 1, right? So in that case, A. Yeah? A is the basis network. Yeah. And then now these are all equivalent IFN. Can you see? A, B, C, and D are all equivalent IFN, but they have different scaling only. Huh? So this is the minimum is 1, right? So B, the minimum is 1. So this is minimum integer. Okay. Unit IFN. It is also cardinal network. Yeah. So, and then if we multiply this by 2, you will get network C. Yeah. So network B, if you multiply by global scaling 2, you will get network C. From network P, if you multiply by 3, you will get network D. Okay. Yes. B is scaled by 18, that's correct. From the basis network, B is scaled by 18, that's correct. Yeah. So now let's discuss about invariant. This is beautiful mathematically. Okay. So IFN equivalent preserve many invariants. Okay. But let's get the pattern about this kind of invariant. I think I make a mistake in the typing. This must be more. Okay. So the coefficient variation of flow, okay, coefficient variation of mortal variation of flow, minimum divided by maximum, or the other way around, average node entropy, network entropy, practically any entropy, yeah, including if you calculate the relative entropy, it will become 0. Yeah. And then if you calculate the cross entropy, it will reduce to become network entropy, and including the mutual information. Yeah, we will not discuss all of that, but let's discuss a few of that. Yeah, what is the actual pattern? Suppose you have two networks, yeah, N1 and N2. Okay, there are two ideal flow network, and then now this Greek notation, yeah, S probably as a positive global scaling. Yeah, so then you will have this value. Suppose now you have another parameter here with this, say, let's call this rho. Yeah, rho 1 and rho 2. Okay, they are any first order statistic. Do you understand the meaning of first order statistic? That means you get from the data, okay, you can get the statistic. For example, the sum, the standard deviation, the mean. Okay, these are first order statistic. Yeah, from this flow, yeah, respectively N1 and N2. Okay, then yeah, if N1 is equivalent to N2 by certain global scaling C, yeah, then the rho is also multiplied by the same scaling. So if you take the ratio of the same first order statistic, yeah, you will exactly get the global scaling. Okay. So now these are the first order statistics. Yeah, the link flow is first order, total, minimum, maximum, mean, standard deviation, median, IQR. These are first order statistics. When we say second order statistic, okay, we get this value, for example, from the first order. Range is minimum, maximum minus minimum, right? So they are not from the data. So they got from the first order. The same thing with COV, coefficient variation of flow, okay? Coefficient of variation. Coefficient variation is mean divided by standard deviation, or standard deviation divided by mean. Okay? This one is IQI divided by median. Yeah. So any statistic that actually come from first order, say any ratio of that, okay, this is called second order statistic. Now, the global scaling is actually the ratio of the same type of any first order statistic. Okay. Now, if you have second order statistic, okay, then made by the ratio of the first order statistic of the flow, then these are invariant. Yeah, this is the invariance. The second order statistic is invariance. Okay. So let's, okay, this is the proof. You can read by yourself mathematically. So let's start with the example so that you can see this. Yeah. Say I have a transport network with only 6 nodes here until F. Okay, and I get this ideal flow network. Can you see? This is already ideal flow. Yeah, 2, 6. So this is pretty much it, right? And the total flow here is 38. So then this is theory. Okay. In reality, the total flow is given already, which is 17,500. That's the demand. So how can I get the actual flow? Okay, so in that case, you just divide. Yeah? So 17,700 now divided by 38. Okay, and then you multiply its value in here to get the link flow. Can you see that? Okay, easy, right? Yeah, the flow itself you get from the network. Okay, but when you want to calibrate, so this is why we discuss for equivalent, because when you want to do calibration, okay, that depends on equivalent, the theory of equivalent of IFN. Yeah? Okay, is this clear or not? So the same thing here. A while ago, we have the flow matrix from basis network. Yeah? So if you multiply by 49, you get the cardinal network here. Oh, wait. Is this cardinal network? Yeah. Yeah. Hey, this is interesting. The cardinal network here, the minimum is not 1. Okay. So the minimum is not 1. But this is already minimum. Okay. So cardinal network is not necessarily unit. Yeah. Okay. Now, in the next few slides, okay, this seems like as if this is not IFN, but actually we have a cloud node here, okay, and then the cloud node is hidden, okay. There is a cloud node and dummy links, okay, but they are hidden from the view of the person because we are using this to compute certain part of the network. Okay, so how to get this card from this flow? How do you get the cardinal network? Cardinal network means the minimum integer. Any idea? Yes. Yeah, correct. Win Sanchez. Yeah. So you multiply by 2. Yeah. Why? Because if you put this into fraction, these are divided by 2, right? 1.5 is 3 over 2. 2.5 is 5 over 2. Yeah. So in that case, the denominator is 2. So multiply by 2. Okay. Then you get this. Okay. Cardinal network. Yeah. Again, don't forget this is actually contain some cloud node here. Yeah. That I did not draw. Okay. So, and check here, the cardinal network is not necessarily 1. Okay. Now, my question, if this is 3 and then this is 4, what is the flow in this cloud? What is the
Come
flow?
again, sir. Come again, sir. Where is the 3 and 4?
Coming here. This is 3, right? Coming out, coming to this end node here is 3 and 4. My question, and the cloud node, okay, what is the value of the node? Of course, easy, yeah. So if you're coming in 3 and 4, it coming out here must be 7, right? Right. So in this case, because there is no other way, so in this case, this is must be 7 also, right? Easy. Okay.
7.
Yes. Yes, 7. Easy. Okay. Very good. So now imagine again the cloud node and dummy links are hidden in all this network. Okay. So again, can you identify which one is cardinal network? What is cardinal network? Minimum integer.
Top left, sir.
The
It's
first
the
one, the
cardinal.
upper right.
Yeah, the
Upper left.
first one, yeah. The first one is cardinal network, yeah. And now, given this cardinal network, what is the scaling? What is the global scaling of this P and C and D? Okay. So D is clearly, if you have 1 here, this is 0.3. So this is basically divided by 3, yeah. So this is actually the scaling, right? How about this one? Yeah, this is actually the scaling, yeah. And how about this one? This is the scaling. Yeah. You look at the 1 in here, okay, and then compare. Okay, these are the scaling. Because this is global network, so once you multiply by one certain scaling, the rest is the same. Simple. Okay. Right. At the bottom. B is not 3, Rafi, is 1/3. Yeah, C is not 2, but 1/2. Yeah, the scaling can not 0, not negative, but can be less than 1. Yeah, the scaling can be less than 1. Right. Okay, so you get it. So we can also get the coefficient variation of the flow. Yeah, what is that? The standard deviation divided by the mean. Okay, or we can also calculate the node entropy. What is that? From the stochastic matrix, you take the ln and then you multiply and then you sum all and then you divide by the number. Yeah, that's called average node entropy. They are also equivalent. Invariant. Yeah. So what's the meaning of invariant? So let's take example in this network. Okay, a while ago, the one that we used a while ago. So this is the top left, top right, bottom left, bottom right. Yeah. So these are the global scaling that we just discussed, right? You just mentioned a while ago. So let's take the average of the flow. Yeah. So if you take the average of the flow, they are different. Can you see? They are not the same. Yeah. The same thing, if you calculate the standard deviation of the flow from all links, okay, they are also not the same. Okay. Right. They are not the same. Okay. But look at the interesting part here. If you divide, okay, remember standard deviation divided by the mean now. If you divide standard deviation with the mean, okay, you will get all the same value. Okay. So can you understand the meaning of invariance now? Magic, as if by magic, okay? So if you, even though they are different, okay, but they are actually invariants. Okay. There are certain measurement that you can see they are invariants, yeah, regardless the global scaling. Okay. So let's get the, okay, now this is the most important part, okay, the application, right? So in transport network, what you have is capacity matrix, yeah, C. Okay. So, and then what you will have initially, because you don't know the total flow, right? How can you know the total flow in the whole network? You don't know. Okay, no problem. I will just, because I don't know, I will assume total flow is 1. Okay, you don't like 1, you can put 100, whatever. No, there is no problem with that. Okay, so let's make assume we use basis network. Yeah, so meaning the flow is probability. Yeah, so mean the total flow in the network is 1. Assume, no problem. Okay, so initially you have from C, capacity matrix mean the number of lanes or the road width, you know. Okay, and then we don't know the total flow, so we just assume anything. Okay, so in here I put 1. So you can get the ideal flow matrix. Yeah, let's call this F0. Okay, now you get the congestion matrix because congestion G is just F divided by C, isn't it? Other one division only. So it's length divided by the next entries. Yeah. Okay. So you get the congestion matrix G0. From G0, what you will get? You will get the maximum congestion. Yeah. The maximum congestion is let's small g. Okay. From here, you get what is called global scaling factor. Okay. So K1 equal to K0 with this one. Yeah. And this is actually the maximum congestion. Okay. The maximum congestion now become the global scaling factor. Okay. So next, now you have the compute. Okay. F1. Okay. You can compute F1 based on this K. Okay. With the same C. Okay. Then you will get new maximum congestion G1. Yeah. From there, look at this, the interesting part. Okay. Now you have, those are the basic. Okay. Now what happened if you have two scenarios? Okay. We call this base scenario and alternative scenario, isn't it? Okay. So for the base scenario, I put superscript B here. Okay. So again, the same thing. Okay. You have K0, which you don't know. Okay. So I put K0 equal 1. I calculate the maximum congestion and get the maximum congestion G0. Okay. So then I want, okay, the maximum congestion G1 with this alternative. Okay. So to be this value. Okay. Then I can just simply put this as the one that I want. Okay. Because I know K0 is 1 in here. Initially I put G0 I can compute. Okay. And this is the target that I want. Then I can get K1. Can you see that? As if by magic. Okay. Even though you initially don't know, but because you know the maximum congestion that you want as your target, then suddenly you get the new ideal flow matrix, okay, based on this K1. Okay. Of course, you can test, okay, it will always give you the maximum congestion that you want. Okay. This is the basis of calibration. So if you don't know, you can set maximum congestion. You don't have data, right? Okay. So if you don't have data, so how can we get? Because we use relative here, so you need to know, or you can set the target. Okay, maximum congestion. Say for maximum congestion is 0.9 or 0.8, for example. You can set. Okay, and then because you know that target, then you can get the total flow. Yeah, because you know the total flow, then you can get the flow. Okay, which will come back to maximum congestion. Is this clear or not? It's nothing to absorb. Okay, so now remember you have two scenarios. Okay, with this one is called base scenario, the other one is called alternative scenario. Okay, so remember initially you said K1, right? Initially, you set K1. This is your base scenario. Okay. Now, when you want to do alternative scenario, which is after some policy, okay, say for example, you widen the road or you reduce the number of lanes in the road or whatever policy that you want, certain change. Policy means certain change that you do to the network. Okay. Okay. Now, after you do certain policy to the network change, isn't it? So let's call this, instead of CB, now I have CA. Yeah? A is alternative. Yeah? So based on this new network, okay, CA, I can calculate the new flow. Okay, but what is the basis of my new flow? This is the most important part. The basis of new flow must be based on the same as the base scenario, yeah, K1. Okay, why? Because you don't change the demand, isn't it? Okay, you don't change the demand, so they must have the same demand. So in this case, K1 become the invariance. Yeah, so K1 is our invariance in all scenarios. Yeah, that's the meaning is you don't change the demand. That means this between base scenario and alternative scenario, okay, they have the same demand, or probably they are implemented in the same year. Okay, of course, our expectation is the alternative scenario after certain change must be better than the base scenario, right? So in that case, okay, so say after this you get G1, okay, and then the maximum congestion is called GA, G of the alternative. So of course, your expectation is this one, right? So the maximum congestion of the alternative scenario must be less than the target maximum congestion. Oh, now you can see how simple it is. Okay, first you don't know the total flow. Okay, then you set a target maximum congestion G1 star, whatever it is, it doesn't matter. Okay, next you have the alternative scenario which you compute. Now what you will do is you compare the new maximum congestion, GA, with the target that you set, G1. Okay, if the new maximum congestion is less than the target that you set earlier, then this policy is better than the base. Okay, if the GA, okay, if the maximum congestion is actually larger than the target that you set, then of course, this policy is not better than the base. So can you see the whole thinking here? Okay, you don't really need data, isn't it? Your data that you need is actually the network itself or the number of lanes. Okay, but you don't need OD data or even flow data. Why? Because all you need to do is setting any value of G1. Okay, and then you need to have two scenarios, base scenario and alternative scenario. Okay, and then you can start to, of course, with certain policy that you want. Okay, these are the main part is actually the policy. Okay, the human part. Okay? This is the part that make you urban planner or transport planner, right? The policy itself. Okay, so then the computation, okay, is just plug in, then you can just check whether this is actually better or not. Okay, that's the whole thing. Any idea? Any comment? Any critics? So if the alternative scenario is higher than the base scenario, oh yeah, of course. If the alternative scenario, okay, congestion is actually higher than the target, okay, than the base, of course you need to change your policy. That means your policy failed then you need to find another alternative. In fact, this is the hardest part in the project, you know, to find the correct policy that will get this passed to this criteria. Okay, this is what make you urban planner. This is what make you transport planner. Okay, is the policy. Then the computation, oh, this is not correct. Oh, this is not correct. Once you can get less than, okay, so the GA is less than the target. See, target is 0.9 or 0.8. So you get 0.7, 0.8, or 0.6. Good, right? Oh, I already improved the congestion. And then all the policy that actually make the congestion less than the target is called feasible. Yeah, this is called feasible policy. Okay, so can you see that you will generate many policies? Okay, and then you check, you set any target, say 0.9, usually 0.9, 0.8, yeah, and then or 1 if you want. Okay, then you check the actual maximum congestion in the alternative scenario is actually less than the target. Okay. Yes. So then you have feasible policies. Yeah. You have feasible alternative scenario 1, 2, 3, 4, and so on. Then feasible does not mean optimum, right? So your goal is actually to create the optimum. What is the optimum? Among all these feasible policies of alternative scenarios, it is all actually less than the target maximum congestion. Okay, which one is actually the minimum? Right? They are the optimum. And you see, we are going, okay, beyond just one alternative scenario, and then you compare, oh, and then you said, oh, fail, and then I stop. Oh, come on. You are not urban planner yet if you cannot even find one feasible solution. Okay. Our goal is not just finding one feasible solution. Our goal is to find optimum alternative policy. Clear? Yeah. Yeah, the scaling, yeah, the equivalent IFN is very helpful. Correct. So because if you don't have the demand, yeah. So how reliable is IFN improving the policy? You can check on your own. Okay. So the reliability depends on the actual value based on the prediction compared to the data that you have. Okay, and then you compare how far it is from the actual data reliability. Yeah. So if they miss the target data that you have eventually, yeah. So then you will say the certain value is not correct. So in that case, you need to calibrate with better model. Okay. So probably your scope is not enough. Probably the model parameter need to be changed more. Yeah, there are many more parameters here aside from the total flow that I did not even mention yet. Okay, but if you check the IFN transport, there are many parameters there. Okay, so these are just one main parameter, okay, with this kappa total flow, okay, that you can actually calibrate. Yeah. So, but how do you calibrate is based on equivalent IFN. That's why the whole theory that I explained a while ago, yeah, is to back up the values here. Okay, this is clear. Okay, so let's practice ya. So these are the, can you create random capacity matrix? You have IFN Excel add-in, right? So you can create random capacity matrix. Okay, and then you can compute the stochastic matrix of the same. Yeah. So you can get the basis network, you can cap network, cardinal network, and so on. Okay. And then you can test the invariance of this equivalent IFN. Can you do that? Okay. Okay. Because you have a matrix, what you need to do is to get the actual positive value. Yeah. You don't calculate the zeros because what we calculate is actually the link flow. Okay, does not include the zeros. So IFN Excel add-ins already have these functions. Okay, to get the positive value. For example, average positive, we will get only the positive entries of the matrix. Okay, so coefficient quartile variation positive, that means you will get only the positive values of this matrix M. Okay, the same thing, coefficient variation positive, you will get this. So if you use just count in Excel, you will not get the correct number because it will include the zeros. Yeah. So count positive will only count the positive. The same thing, average positive, okay, will get only the positive one. Standard deviation positive will only get the positive value of the flow. Okay. So try to make a random network. Okay. So if you can finish this today, you can do it. If not, we can put this as assignment. But I think you can just practice this in 5 minutes. No? So create a random network. Yeah. So capacity matrix, random capacity matrix. And then you calculate the stochastic matrix. Yeah? And then you calculate the ideal flow. Okay. And then you scale. Yeah? From calculate the average flow, standard deviation, and so on. Okay, can you find the invariance? Okay, if you are familiar with Python, you can also use this kind of function. Yeah, see, if you look at the computation of scaling, it's just simple. Yeah, I'm using NumPy here. Okay, so let's practice. Can you? Create any say using Excel. Okay. Okay. So I give you example. You can also do the same thing. Yeah? Screen 2. Can you see my Excel here?
Yes, Doc.
Okay. So all you need to do is type this one, N underscore R&D capacity. Okay? And then you highlight the whole things. Okay, for example, I have here 4x4. This. Okay. And then click Shift Control Enter together. Okay. So once you get that, okay.
So Kardi, again, so the shift control enter, correct?
Yeah. Let me demonstrate to you with the new sheet so that you can see. Okay. Equal N underscore R and D. Now, this one, yeah. Random capacity. So you put tab, okay, and then close it here like this, right? And then what you need to do is use determine the size. So what is the size? 3 by 1, 2, 3, 4 or 5. Yeah, 1, 2, 3, 4, 5. Okay, so this is the 5 by 5, right? Must be square matrix. And then you click here. Okay, and then shift and control and enter together. There. Okay, so this is random capacity matrix.
Okay, sir, got it.
Okay, got it. So now what happened is, if you put here in the formula computation, calculate now. Okay. Every time you press this one, it will create random new values. Yeah. So if you want to draw the network, you can. So you can just put the node, right? And then you can just put X and Y. Yeah. So we have how many nodes here? You have A, B, C, D, E. Oh, 5. Okay. Okay. So in that case, we can just put any value here. So I will define the shift just to draw. I will put maybe 50. Let's try that. So A is just, I will put 50 and 50. Later can change this one. Okay. Let's call this shift. Okay. So then this one plus shift. Same thing, I can just put any value. And then you can draw the network, right? So N underscore draw network. Yeah. So draw network, you calculate the capacity matrix here. And then this one. Okay. Yeah, of course this is linear. So then you can start to change this. Yeah. So for example, I don't want there. So I want it a little bit to the right. So let's put this 300. Oh, kurang. So 500 maybe. Okay, so I can change this value so that it will go to whatever. Okay, I will put it here. So this is Y is 50. So then this is plus shift, maybe 2 times shift. Okay, so this is the same thing. Okay. So P is where you want to put the P. P is the same as this one. So this one is equal to 900. Maybe the same X. Okay, but this one is 3 times. 3 times. There, a little bit better. All right. So you can just adjust the coordinate to draw this one. Yeah. So once you have the capacity matrix, what you will do, you calculate the. Yes, Rafi, you want to ask something?
Yes, sir. I just was to ask what is the command to draw that network, sir?
Oh, this one. Draw network.
Thank you, sir.
Yeah, the draw network, you get the matrix and then the coordinate, yeah, including the nodes. Okay. So once you have that, so you can get the, say you want to get the, say, let's say I have the kappa here, I will put here, yeah, kappa. Okay, the one that I target. For example, I will put 100. Okay. So then I have n underscore capacity to ideal flow. Right? So I have capacity to, this is the capacity, and then the kappa is here. And then close it. Right? Now you need to make it into the same size. What you need to do is you sieve and then arrow going down 1, 2, 3, 4, 5, right? Same thing here. So press there and then shift control enter again. There you can get that. Yeah. So this is my new ideal flow network. So you can, this is the target kappa. So let's get the sum here so that you will see. Okay. And this is also the sum. So this is random. So okay, you will see that the sum is pretty much it, right? They're all the same. Okay. And then the total sum in here, of course, according to your target value, 100. Okay. Now, if you want to get the unit max, so you just put cup network. Okay. If you want to get the basis, so you just put basis network. If you want to get unit mean, so you can just put unit network. Okay. If you want to get unit average, so you just put mean flow network and so on. Yeah. So now you get the value. Okay. You can get the stochastic from this. You can also get the, for example, I want to get the coefficient of variation. Okay. So to get the coefficient of variation, I can calculate like this. Okay. The average divided by standard deviation. But if you do like this is not correct. Why? Why this is not correct? Because this includes all the zeros. Can you see that? Yeah. This value is including in the zero. So this is not correct. So to make it correct, you need to get only the positive. Okay. So how to get the positive? Yeah. The positive, you get average of positive, of this matrix. The same thing, you get also the standard deviation of the positive. Okay. And then from that standard deviation positive and average positive, then you can divide. So I can divide. Okay. So this one, standard deviation divided by the mean. Yeah. Both are positive. So in that case, I get this value. Yeah. In this case, because I did not make it, so this one is 95 over 130, right? So the same thing, if you calculate the same thing here, coefficient variation of this unit max with the unit mean, okay, and unit average here, okay, and unit median, unit standard deviation, and so on. Okay, unit QSUR, you can calculate everything, and then you will see, okay, even though they are equivalent IFN, one is probably different, but they are invariant in terms of COV plus, which is coefficient variation of the positive flow. Okay. So the same thing, if you want to calculate the entropy and the others, you can also calculate everything. Yeah. So up to here, is there any question, anything to discuss?
The Kardi question regarding the assignment. If you will submit the assignment, sir, is it in the Excel format?
Yeah, in Excel, but something like this, just something like this.
Okay, all right. In PDF, it's okay.
Yes.
Yeah, just
no,
the whole file.
Yeah.
All
So
right, all right.
how I know that you compute correctly? If
Ah,
you
okay, all right. Okay, thank you.
right, okay, you see something like this, you can calculate, yeah. So yeah, these are the oh no, this is different thinking. This is later after this, the decompose and composition. Yes, someone asking you something. So equivalent IFN, done. Copy of the example for the reference. I thought the copy of the example must be your what is that called? The assignment, isn't it? Yeah, yeah, asking me the give me the example. The draw network command did not work. You want to show your screen? I can help you.
Yes, sir.
Um,
For a while, sir.
Share your screen.
Sir, the homework is on Excel, or can we also use the Python?
Yeah, if you don't like Excel, you can use Python. That's okay.
Thank you.
In fact, I have an in PyPy. If you are using Python, you can pip install ideal flow network. You can get the whole things in Python already. So, okay, run network. Okay, open parenthesis. The whole C the network from P5 until no.
So Rafi, your syntax is n underscore lang dapat.
This one.
Tanggalin nyo ng n minus. Yan, Sir Rafi, tama.
Okay.
Yes,
So
sir.
you highlight that.
Then,
Open parenthesis and then this one, the whole.
including this one, sir.
Yes, from there.
Then close
No,
parenthesis.
not including the label, not including the label from here until here only. So A5 until F9, is that correct?
A5 until
Eh?
F.
No, not P.
B5,
B5 until F9.
F9.
Yes.
Then close parenthesis.
No, comma.
Oh, I get it.
Comma. Okay.
Then this
And
one,
then this one. Okay.
including the node.
Including the node. Yeah, because and then close parenthesis.
Then shift control.
No, just enter. Yeah.
Yes, sir. Thank you, sir.
You got it. Okay. Very good. Okay. And then you can yeah, this is just visualization, so not so important. Yeah, but it's fun.
Yes, sir. I will just stop my
Right. Thank you. So anyone else have problem and you want to practice first little bit or
Yes, please, sir. Practice.
okay, so I give you a few minutes to practice. Maybe 5 minutes is okay.
Yes, sir.
And then you ask question. Okay. Yes.
Sir, can you repeat the one with the nodes before you draw the network?
Okay, the initial. Okay. This one.
No, sir. The one after shift. The nodes, yes. The
This one?
coordinates, sir. Yes, sir.
This one is just to draw. So this is not so important.
Okay.
So the most important is actually this one.
Okay.
Okay, so you need to get the random capacity, okay, and then test the different type of equivalent IFN, yeah. Either cup network, unit average, unit median, unit standard deviation, and unit IQR. Okay, yeah, QQR. You in here you will see if we use the unit COV and unit CQR, they are not one, yeah. Okay. No, this is not because they are equivalent. This is already invariant, so this is practically useless to calculate this unit. And then you can also use the others.
Thank you, sir.
Okay, you try first, huh? Okay, 5 minutes. and fix the drawing. And so depending on the coordinate, so you can get better result. Okay. With this, we can actually change the values. Okay, the network will also change. So when you're done, you can share your screen. Maybe a few of you. You can tell me if you have any problem. You can solve it together. Mhm. Dan, I will show you a certain screen here. Can you see my screen? Yeah, this is the model. Okay, so if you refresh, reload this page, okay, under the ideal flow network, at the bottom I have an Excel file to redistribute the congestion. You can download that. So example. Inside that have two sheets, yeah, sheet 1 and sheet 2. So in sheet 1, okay, you will see these are the number of lanes that we put. So you have like base scenario and then the alternative scenario. Okay. So this is actually the same thing exactly, except this node, yeah. This is 7 lane and then now become 4 lane. Okay. So, and we can calculate, okay. From here you can calculate, say I set the kappa 30,000, meaning the total flow in the network is the same, both scenario, yeah, C1 and C2. Yes, Archie.
Doc Kardi, I'm getting a problem. When I open the sheet number 1, there's an error. Can I show my screen so
Oh,
I
sorry.
can, yeah, sure. So if supposed to be like this.
Did you have
Can you,
Excel? Okay.
oh, oh,
Okay. See, this is because the address still in my. So you just remove this. What is this? The name in my username. So you can just put it in only equal and then okay, you remove everything until n. No, until n.
until end. Here.
Yeah, that one.
All
There.
right. Okay.
You
Uh,
there. Okay, no
okay.
problem. Okay, so then you highlight and then you change that.
All right. Okay. Got it.
So it's
Thank you.
the error happened because it go to my folder,
There's a
but
link. Yeah, there's a link there.
it should not be a problem. Okay, yeah, you need to modify a little bit. Just remove the folder name. Okay, and let's come back there. What happened is say I set the same demand, okay, but in the base scenario, DP, link DP, so this is a link, have 7 lane, okay. In the alternative scenario, link DP have 4 lane only, so all the rest are the same. Can you see this? Okay, and then total demand is the same, okay, and then we in transportation usually this is in PCU, right? Vehicles per hour per lane. Okay, so you can set any value here. So I set the maximum speed and distance. Okay, and we can calculate the from capacity to ideal flow with certain value kappa. Okay. And then here is, I just use traditional way. Instead of calculating the actual congestion, I calculate this congestion based on capacity factor. So if B is equal to 0, okay, so that means no link. Of course, the matrix must be 0. Otherwise, get from the flow divided by the capacity, number of lane multiplied by capacity factor. That means number of vehicle per hour per lanes multiplied by lane. So in this case, that G congestion become unitless, no unit. Okay, because this one is vehicle per hour. Okay, so this is VC ratio or saturation, degree of saturation, or they call that congestion ratio. Yeah. So then you get the maximum, okay, of this one. Or you can get the average if you want. Okay. Should be average positive, right? So not just average. And I developed what is called FAR-Pi index, or FAR-P index. Okay. This is an index to tell how close the capacity, this is to say how close is the capacity to the pre-magic capacity. Remember, when we have the pre-magic capacity, that means the whole network is already in equilibrium. So in that case, you will have FAR-P 100%. Yeah, here, this one. This is actually already pre-magic. And interestingly, this is to tell that the number of lane I reduce, right, from 7 to 4, all the rest did not change. Okay, and the performance is actually better. Maximum congestion is 93%, and then reduced to 83%. Okay, but if you calculate the visit on travel time, okay, travel time is 443. Okay, I don't know what is this in the units. This is based on these values, maybe in minutes. Oh, this is in seconds, sorry, multiplied by 3,600. Okay, so the travel time here is in seconds. So the average travel time 400 something. Okay, and then here is actually larger. Yeah, so if you just look at the travel time, yes, the average travel time is actually worse for the second scenario because you reduce the number of lanes here. Okay, but if you look at the values in the congestion, okay, so you will see that the distribution is the congestion is actually redistributed. So the 93% reduce, become 83%, then 85% increase to become 83% also. Okay. And if you look at the travel time, they are all the same. So this is what I call this mass equilibrium, isn't it? So where you go, it doesn't matter. Okay, it will always reach. You will use the same number of travel time. When your capacity is pre-magic, you will get that mass equilibrium. yeah, which is the same as social equilibrium. Okay. So now my question, which one is better? So if you look at only based on average, this is actually worse. Okay. But if you look at the overall performance in the network, this is actually better. The same thing with the second scenario here, sheet 2. Okay. Initially, I have 5 lanes here. I reduce it to 2. Okay. Again, just to demonstrate, this is not pre-magic, so is it better or not? No, actually, this is worse. Yeah. So not necessarily reduction of number of lanes is getting better. Yeah. This is actually getting worse. In terms of maximum congestion, oh, better. Yeah. In terms of maximum congestion is actually better. 84%. Here is actually 79%. Yeah. But if you take the average, this is actually higher. So the same thing with the travel time. Okay. Travel time less is better. So this is less than this one in terms of average. Okay. So again, you can see that when you reduce number of lanes, okay, that particular place increase so much, okay, but certain place is actually reduced, and so from 84 here now become only 79. So this is how we analyze the whole network rather than just analyze one particular link. Okay. Some congestion will be shifted to another because you improve certain road. Okay, the other road will get higher or lower congestion. Okay. Any question? So I don't recommend to use average. Why? Yeah, I recommend to use maximum rather than average. That question is why, right? So if you use average, it seems like better on the average, but you cannot actually check the correctness. Average is the whole network, but now you change the network, getting bigger, you get a lower average actually. Okay? So it depends on the scope of the network. But once you get the maximum congestion, the maximum is always there, the same thing. So, and maximum have two good things. One is once you get the maximum, you will get the actual location. Where is the maximum? That means you can actually test on the field, okay, on certain year, whether that particular link is actually has maximum congestion according to the prediction that you calculate or not. That means reliability of the model can be verified. But when you use average, how can you verify the entire network? You don't have the tool to measure. Okay. the actual traffic flow in the entire network, isn't it? So that is the problem with the average. Okay. There is no feedback loop to test whether the model is correct or not. Okay. By using the maximum, you will know the location. Okay. And now, based on the econometric model, you will get also the time when it will happen. So in that case, you can verify your plan, whether it is true or not. Okay. Science that based on average seems like very nice, okay, like the global warming and so on. So, but at the same time, verification of this kind of science is very hard to test. Okay, unless you really have the whole things to measure. While if you use the average, the maximum, you can easily locate where is the actual location. Then verification is easier. Anyone want to share your screen on the practice a while ago?
Sir Kardi, I have the problem in the file that you gave to me. I'm trying to delete the link, but there's a prompt saying that I cannot delete the
Oh, okay.
invalid, something like
Okay.
that.
So what you need to do is you get the correct one. Okay, you get the correct, and then you Control C, copy. Okay, and then you highlight the whole array because you cannot delete the array, you cannot edit the array.
All right, okay.
Okay, you get the entire array, use arrow, and then you use Shift, Control, Enter.
So that, all right, okay.
Okay, you Control
How
P
to-
first, and then you go Shift,
Okay,
Control.
so
Or you can just delete that array, and then because you already copy, right, the correct one, then you can again highlight and then Shift, Control, Enter. Array in Excel cannot be edited. I understand that problem. Yeah. So for the two scenario, what will be our consideration? Yeah, I just mentioned a while ago. Okay, so consideration. For me, I choose maximum congestion over the average travel time. So why? I give you several arguments a while ago. Okay, when you take the average, seems like okay, but actually that is not okay. Why? Because average you cannot measure, you cannot verify in the real world. Okay, it seems okay with the average. Okay, but the question is, how are you going to verify the average of the entire network with the data? There's no way. So this is the science of lying. Just use average. Actually, there is a book, How to Lie with Statistics. This is one of them. Okay, one of the technique of lying with statistics is to use average. Okay, so if you want to verify, use maximum. Okay, so there is another branch of statistics. It's called robust statistics, and which is really based on robustness, verifiable. Okay. So the basis of science is when you model something, right? After you model, someone else can check your model is correct based on certain assumption. Yeah. And then someone else can also check on the field whether the value of the data is verifying your model. So the whole science is correct because of verification. But if you cannot verify your model on the field, so how can you tell that your plan is correct? This is very big question mark. So I understand I against the majority. Okay, but mathematics does not lie. Okay. Unlike statistics. Yeah. Aside from these jokes, but there is some truth on it, isn't it? You cannot calculate, you cannot verify the average of the entire network in the city. There are more than 1 million links. And how are you going to get the flow of those 1 million links? Our monitoring system is not that good yet at this point. So, but using maximum, you can get only 1 or 2 links. This is easily to verify. Yeah, the view is debatable. I understand that point. Yeah, so getting OD flow is again rough. You mostly use center of the district or something, right? And then you're telling that this is the truth. But people change dynamically, and then you're telling this is the truth. You keep insisting that this is the truth. Is there any way to verify that this is the truth? There is no way. So then again, I don't like the science of approximation which cannot be verified. Okay, so let's develop science that actually can be verified using data. Okay, the model must be verified using data. Another question, in proposing alternative, okay, is it okay if pre-magic criteria? No, of course. Pre-magic criteria is the hardest part. In fact, okay, in 2017, I changed the entire network inside Atheneum. Okay. So we create the model and then we make it 1 week. Before it was 2 weeks. And in the following follow-up, they asked, is there any way we can improve better than this? This is actually already much better. Yes, we can. So I computed the way to compute pre-magic capacity. We know pre-magic capacity is the best. Okay. So, and I computed all the entire network. This is supposed to be from less number to larger number. And the committee who supervise all of this telling is impossible. This is too expensive to change. So in that case, if you have new city, make it pre-magic. But if you have already the city developed, to make it pre-magic is very expensive. And okay, I will show you the one in let me check if I have Premier Network here. Okay, so you go to IFN Virtual Lab. I will share you the screen. Yeah, this is connected to the next topic that we will discuss. Can you see the screen here? So if you go to IFN virtual lab here, okay, then go to this page, and then you go to Premier Network. Okay, so you will get this page. So you're supposed to read, and there is a lab session. So in here I have capacity matrix. So if you click this, it will create random capacity matrix. Can you see? Yeah, this is random capacity matrix. Yeah, this is the pattern of this capacity matrix. Okay, and now because this capacity matrix is irreducible, so I will show you. Is this irreducible? Yes, this matrix is irreducible. Okay, because this capacity matrix is irreducible, so we can get cycle. Okay, so you click this one, you will have cycles. So these are the cycles. Okay, so you change and then the cycle will change. There. Oh, this is only one cycle. Okay, let's change this to 5, for example, and get the cycle. Oh, you have only one cycle. Okay, I will add 1 in here, for example, and then get cycle. So you have 2 cycles. Okay, these are the number of cycles in this capacity matrix. Okay. Now, ideal flow network can be developed based on cycles. Okay, so if I include all the cycles there, okay, so if you click this, it will check all the cycles because I have 2 cycles. So then the matrix will be this way. This is the IFN. You can see this is the IFN, the pattern, yeah. The pattern, and this is pretty magic. Okay. You can also test whether this is pretty magic, yes. Okay, irreducible, yes, and then ideal flow, yes. Okay. Now, if you click this, okay, if you click this one, this is an optimization. Oh, not open. Okay. Oh, sorry, I'm not working. Why it was working? Anyway, if next time I will improve this. I think there is some bug that make it not working. Oh, there. Oh, okay. So there is some bugs here that I need to fix. So if this is working, it will optimize and then calculate the change between the capacity matrix and the ideal flow matrix. Okay, in order to make so that the change, the number of lanes will be as minimum as possible. Okay. So we know that ideal flow matrix is pre-magic, right? Well, this is the real actual condition. So then we want to know what change we want. So this is from 6 lane now become 4 lanes, right? So 6 lane here, if you want to make it very magic, you need to reduce 4 lanes to become 2. And then from this one 1 lane you need to increase become 2 lanes. And so on. Okay. So there is if we press this one, so this is new capacity matrix. Okay. See, I add here, for example, 1. So clearly this is irreducible, but this is not pre-magic. See, this is not ideal flow. Yeah, capacity matrix is not ideal flow. Now, from there you can get a cycle. Okay, so for example, these are the 2 cycles. that create this network. Okay, so you can see this. Let me, oh, oh. And then I can click this, add premier cycle to buffer. There, these are the premier cycle to buffer. Okay. Premier cycle means I will add the number of cycles to buffer. These are the cycles. Okay. And then I will create, because of that, I can add here. So add AD and then ADCB. So then this is the actual ideal flow network. Okay. This is called premier ideal flow network. Okay. Premier ideal flow network is developed based on cycles of the capacity matrix. Okay. Is this clear or unclear?
I think we need to practice the again. To come back to practice everything.
So, which part is unclear? In forecasting the future AADT, is it okay to use traffic growth rate? Yes. If you can use, okay, in transportation, they use very simple growth rate, or I think the better method is to use regression. Okay, if you really know how to calculate time series, look at the values in, no, the slide in related tutorials. Okay. If you look at the bottom there, I'll show you the screen. Okay. In our course, okay, at the bottom, there almost the bottom. I have time series forecasting. If you want to forecast your AADT, you probably want to use this one. Okay. Let me open this in the new course. See, this is time series forecasting to do forecast your AADT and so on. Okay, so these are, you can read by yourself. And in fact, if you look at this, okay, I can estimate much better. You see, I can have a forecast better than your straight line, isn't it? Using this technique.
Thank you, sir.
Yes. Okay. Yeah, this is still optional, but and the Excel is here, so you just need to get this. Okay. Any other question?
Sir, I was just to
Okay.
clarify, sir, if our assignments will be same as what you've given to us, sir.
If you finish, we don't do that assignment, but if you don't finish, yes, we will put that as assignment. Is that okay? If you finish during the practice in class, so there is no point to give you assignment. But if many of you did not finish, so I'll just put that as assignment so that you can practice. Okay. Okay, so you want to put that as assignment so that you can practice later. You have more time. Is that
It's
okay?
okay, sir. It's okay, sir. Yeah,
Sir.
it's okay.
Okay, okay.
Okay, sir.
In that case, okay. Okay, good. So let's continue then. What's the next topic? Oh, power dynamic. Okay. So this is nice. So using the same IFN, okay. The way I explain power dynamic, I will give you some brief motivation first. Okay. So I will make it speed in terms of motivation only. This is what you can do. After that, okay, we will go to the detail basic theory, and then we'll come back here on how to compute. Is that okay? Okay, because if I just give you directly theory, you will, oh, what is this? And then after that, at the end, you will start to see the application, and then you don't have motivation anymore at the time. Okay, so let's reverse the process. Okay, to give you the in brief the application, and then go to the theory, and then come back to the application. Okay, just the way to teach so that easier for you. Okay, so you go to the slide of power dynamics. Okay, after that we go to signature, and then come back to the power dynamic. Is that okay? Okay, so this is the power dynamic slide. Okay, so I will start with brief introduction, okay, of brief power dynamic. So you can go to IFN. This is finished, yeah. This one, power dynamic, okay. And then we go to signature, and then come back here. Maybe this is not finished now, it's 47. Anyway, let's go back. Let's go to the power dynamic first. Can you see my slide?
Yes, sir.
Oh, okay. Yeah. Okay. So I will introduce you to certain integer IFN, okay, and then let's discuss about check and balance systems, okay, and then I will go mostly on this application, okay. We supposed to learn integer IFN and application guide, but let's make it brief first so that you will know. Okay, so we will create system engineering, okay, based on IFN, yeah, ideal flow network, yeah, to model influence and power dynamic system. Okay, you are going to create network structure and influence strengths, yeah, that will affect the dominance of decision making system. And then you want to get the check and balance feedback loop, okay, without unnecessary complexity. Okay, so these are the example of application. Okay, how to capture essential relationship, for example, within your own family. Okay, how to make academic research system structure that encourage faculty, students to do more research, for example. Yeah, and how to what is the essential ingredient to make a business to run autopilot? Okay. Okay, how to make the business plan monetization factor and strategies, for example, to create lean up startup company. Okay, these are the example of application. In election, in actual political structure, okay, is direct election where the citizen vote directly to the leader better than indirect election, where the vote go through party? Okay, say in the United Nations, is this what is the actual better political structure for the UN, for example, to have a peace and prosperity than only a few powerful countries play the major role. Okay, so and so on. So these are the example of application of this power dynamics. Okay, now if I provide you with the AI template, 2 pages. If you want to create the the actual things. Okay, all you need to do is just copy and paste this template. You read carefully so that you will know this is the actual things. Okay? You want to propose a minimal, strongly connected directed graph or network to provide organizational check, balance, autonomy, and accountability. Yeah. Okay, this is the meaning of power dynamic. Yeah. So essential of this, yeah, you will have strong connectivity, check and balance. Okay, there is a feedback loop for any, and then minimal number of nodes. Okay, and you should have any good clear meanings. Okay, and then prevent there is a single node domination. Okay, and it is the single node domination here is not necessary in strategic sense. Yeah. Okay, where the focal point is actually for example, yeah, a customer is the ultimate reason that we exist. Yeah, in the government, so the people are the sovereignty, right? So this is still okay. Yeah, not in this matter. Okay, and then we need to have self-regulatory. Okay, so the point is the link represent influence. Okay, and then for your own application, all you need to do is just change the application name and the goal. Okay, so I provide you with the template for your AI. So remember, yeah, we don't have a single node domination. Why? Because single node domination, okay, say that node represent a person, department, or branch of government, or whatever, okay, agent basically, yeah, that can make decision without being checked by the others. So dictatorship is not allowed. So there must be check and balance. Okay, we don't want to have a system that is unchecked, right? In that case, we need to create strongly connected network. Okay, but be careful. Okay, the meaning of this no single node domination does not mean not dominant in central focus. Yeah. So if this is a business, of course the customer must be the focus. Yeah. If it is governmental bodies, so the power must belong to the people. Okay. But this is still can go hand in hand. Okay. So it doesn't mean that when we say customer focus, does not mean that customer can get the free product, seize the control of the company bank account and so on, right? Okay, so the same thing, yeah. So even if power belongs to people, does not mean that people can decide all the budget of the government, right? So the next few slides I will just remove, okay, but we will come back again later on. So first is what is IFN in this case, yeah. So IFN is a model that represents ideal condition. So the story of IFN is the story in heaven. That means certain things that ideal. Okay, that means you can think the ideal things within our reach because we have the tool. Yeah. So why you want to model ideal condition? If you know what is the ideal, okay, then you have the goal, isn't it? So if you know the goal, then you can be effective. Okay, to be effective is much more important than to be efficient, right? So in that case, if you know the goal, okay, then you know how to be effective. Okay, so that means if you know the IFN analysis, then you can get the compass on various view about the actual ideal condition. With that, you can navigate your decision, your policy in the society toward that direction. Okay, that's why the name is ideal flow network. Is that clear? Okay, so even if we cannot reach that goal yet, a while ago you are asking, oh, what if my network is not pragmatic? That's okay. Okay, if you cannot reach that goal yet at this point, Okay, if you continue in this direction, you eventually go there. Okay, so this is a tool to analyze the efficient way toward our goal, because you know how to be effective, then you can be efficient. Okay, so then again, this is the definition of IFN. Okay, and this is actually more than the mathematics. Yeah, by spotting later the loops, okay, the labeling of the node and the link flow to ensure that the balance happen. Okay, and then later you can do what is called pivot analysis. Yeah, recognizing the overlapping between the loops that unify the system. Okay, then you can discover the pattern. A pattern of reciprocity, yeah, pattern of justice, pattern of fairness, pattern of interdependency. Okay, so integrity, basically. Okay, then you can start to see the connection between morality, spirituality, and mathematics. Okay, in the new way of thinking. Okay, so the idea is what flows out must flow in. Yeah, eventually, what we give, we do not lose. Yeah, we invest in the cycle. Okay, in the long term, that eventually come back to us. Okay, so a while ago we already discussed cardinal IFN, right? And later we will discuss more detail about premier IFN. Yeah, what is premier IFN? In using cardinal IFN, you know the stochastic matrix, which is equivalent IFN a while ago. Okay, but if you use premier IFN, you don't need to know the stochastic matrix. All you need to get is only the network itself, which is supposed to be strongly connected. Okay, then you will find the minimum integer based on the connectivity of the network structure. Can you see the difference between cardinal and premier? Okay. Okay. So cardinal network is equivalent. Okay. This is the minimum integer based on the stochastic matrix of the capacity matrix. You preserve that. Okay. While the premier network is the smallest integer ideal flow network for the network structure. Okay. Of course, the stochastic matrix will be different from the cardinal network. So in the middle, we have what is called integral IFN, which is, is also minimum integer IFN, okay, for that network structure similar to premier, but approximating the stochastic matrix. Yeah, why we need to approximate? Sometimes we cannot get the cardinal IFN. That's the problem. Okay, sometimes we cannot get. That's why you, if we want to get that cardinal, then you approximate using integral IFN. Okay, but for our case, okay, we are dealing mostly with cardinal IFN and premier IFN only. Can you distinguish between the two? Okay, cardinal IFN is equivalent IFN based on stochastic matrix, meaning you need to know the probability. Okay, in here, premier IFN does not need to know the probability. All you need to know is only the network structure. Okay, that's the idea. Okay, so now this is example. Okay, suppose I have this capacity matrix. Okay, I calculate the stochastic matrix. Okay, and then I can get the cardinal network, integral network, and premier network. Of course, the premier network must be the smallest. Okay. Now, this is the sum. The blue part here is the sum of row and column. Okay. Now, if you know the vector sum of row, it is because pragmatic, though this is the same as the transpose vector sum of columns. Okay. We call this phi, right? Phi. Okay. Then you can calculate the relative power, which is the same as priority values. Yeah, later we can apply IFN for prioritization. Is the same as this one. So you can get the relative power or priority value, okay, which is simple, yeah, relative node value. Okay, so for example, you can get this phi divided by the minimum of phi, or you get phi divided by the maximum of phi. Okay, it's up to you. Okay. Basically, a relative node value. That is relative power. Okay. So what is the usage of relative power? Okay. Once you get the ideal flow later, okay, of Premier and Cardinal, you can check the change, okay, in structure, change in influence, whether actually they produce how much power. Okay, for example, yeah, certain structural change will still produce the same run in terms of prioritization, but their power is actually reduced drastically. Okay. Let me say this. If you want to model check and balance system, okay, where the authority and responsibilities are balanced, yeah, there is always accountability, okay, balance of power, then you need to use IFN, okay, basically. Yeah, this is example of separation of powers in government, in business, in families. You know? Remember, you need to have what is called shareholder or the agent, yeah, the entities. Okay? They are the nodes. Okay? Nodes can be entities, agents, or can be factors. Okay, up to here, is it clear? Nodes are entities, agents, or factors. Okay, these are the examples. Okay, and then of course you need to create accountability. That means you need to create feedback loop. Okay, so this is the main part that you need to remember. The node are entities, agent, or factors. The links are influence, inform, control, give feedback, monitor, or supervise. Is that clear? The flow represents that strength of influence. Okay. Now the flow in the links represent the strength of influence. The flow in the node represent the power of that agent or that factor. Okay. The technique is to create it irreducible or strongly connected. Once you make this, you can calculate the IFN. After that, there are many analyses we can do. Yeah, we can do Markov, we can do signature, we can do optimization, what if analysis, and so on. Okay. Okay. The most important is to create irreducible matrix, yes, strongly connected network. Okay. Why? Because if the network is irreducible, then the system is integrated, having check and balance. Okay. So there is a cycle of pair that you can have a pivot. That means you can create in the check the interdependency of the system. Okay. So now, if your network is actually weakly connected, remember, if unconnected network, we cannot use IFN. Okay. If your network is weakly connected, what does it mean? Meaning you have source node, sink component, source component, right? In power dynamic, a network with weakly connected, that means you are incomplete network. Okay. So if you have source node, that means dictatorship. If you have source component, the group dictator. Okay. If you have sink node or sink component, they are redundant. So if you have dictatorship, you have unchecked system. Okay. If you have sink node, these are redundant. That means if you remove this sink node or this sink component, it will not affect the system at all. Okay, so in that case, you need to find other node probably or other link. This is how you model, yeah. You need to find other node or other link that will make it strongly connected or irreducible. Is it clear? That your modeling is to create strongly connected. I repeat many times. Yeah? Okay, let's give example. This is in a family. You have family. Everyone have family, right? Let's see this example. Both of them are weakly connected. Can you see this? Oh, the father influenced the mother. The father influenced the son. The father influenced the daughter. The mother influenced the son. The mother influenced the daughter. Yeah, the arrow represents influence. Yeah, but in this network, you see the father is the source. Remember, the source is dictatorship. Yeah, the thing is redundant. Can you see? So the father is the source. Okay, and this son and daughter here are redundant because they are the sink. Okay, the meaning of redundant means if you remove this from the system, it doesn't matter. Once you remove the son and daughter, so I will draw a pen here. This one is removed because this is redundant, right? Then you have no more of this. You have only father influence the mother, but now the mother become sink. Again, the mother become redundant. So now the father is the only node here in the family. So this is the system of one person show, one man show. Okay. So how about this second example here? Okay, the father influenced the mother influenced the father, and then these two parents influence their children. Okay, this arrow represents influence. Is it clear? So then, because this is sink node, so you can just remove. Then eventually your system is only father and mother. Okay, which is strongly connected already. Clear? Okay, so you can remove or you can add. Okay, my suggestion is to add. Okay, this is another example. Say you have management here, and then the management consists of two departments, say production and sales. And then the sales will influence the customers. The production will influence the product features. Okay, the product features will be delivered to the customers. So again, this is incomplete system. Yeah, why? Because this is no check and balance. This is not strongly connected, right? So look at this. The management is the source. So this is practically dictatorship. Again, the customer is the sink. So you can just remove this customers. Yeah. Okay, once you remove this, the two of them become sink. Eventually, only management become the actual system. Okay, if you remove. So this is not good. Yeah, incomplete system. Okay, again, another example of incomplete system. Okay, in the project management. So I have the owner here, which is the source, and I have the contractor. So the owner is unchecked, the contractor is a sink, so this is practically redundant. Okay, even if the contractor now expanded into a system of contractor, again, this is still redundant. Okay, so you can just remove this. Okay, incomplete system. Then the question is how to make it strongly connected, right? So how to make it strongly connected is several ways. Okay, so remember, yeah, you have a network. If this is unconnected, we cannot do anything with it. Okay, so if it is connected but weakly connected, okay, it must have sink node, source node, sink component, or source component. So one way is to add the cloud node. Okay, then with the dummy nodes, right? Then you can with the dummy links, yeah. Then you can get strongly connected. Okay. The simplest way is just add up communication link. Or you can also add another node, which is the target or the goal, the output node. Okay, depending on your system. For example, in the business, the goal is supposed to be in customer. So include customer inside your system. In the politics, the goal is supposed to be citizen or resident. Then include this citizen and resident inside your system. Okay. In the construction, project management a while ago, the goal is to create the building. Then include that building. And remember, building is not person, but they are agent. Okay. So you can include as a node entity. Okay. So I give you example so that you can get clear. Okay. Remember, this is an incomplete system a while ago, right? The owner and the contractor. How to make it irreducible system? You just add up communication. Yeah. Add up communication here. Is it clear? The same thing. Yeah. This is incomplete system in the left. Okay. Then you can make it two-way communication, then become irreducible system. Simple or not? Is it clear? Just make it two-way communication, and then you will get that. Okay. So the same. Another way is to add the output node. Yeah. In this case, the building. Right. The building is the output node. Can you see? So I insisted this initial network because I want owner influence the contractor and so on. Okay, this is within the contractor, and then the worker will create the buildings. The building will influence the owner decision. Yeah, in this. So now we have the feedback loop. Yeah, with this strongly connected network already. Can you see this? Okay, so can you practice? How about this one? Oh, let me remove the link. Can you practice? Okay, a little bit. Just practice a little bit. Important practice, yeah. You must do this. Okay. If you see a weakly connected network, can you make it into strongly connected network by adding up communication or adding output nodes? Okay. Here, these are two examples. Can you make? You can draw here in the Zoom. You can draw here. Can you? Yes, Rafi.
Sir, I cannot draw, sir, at the
You
screen.
cannot
I
draw
can
here.
discuss, sir.
Oh,
Adding some arrow from son to father,
yes,
and son to mother,
yes.
daughter to son.
Daughter to son. Yeah.
Likewise, mother to father.
Yeah, okay. So actually, as long as you can get from one node influence to each other, then you can get the strongly connected. Yeah, very good. How about this one? Can you add links so that it becomes strongly connected? Yes. Oh, she can draw. Very good. Yes, Julian.
Sir, you can add a guidance counselor so that the son and daughter can influence the guidance counselor, and the
That's
guidance
good.
counselor can
Okay.
influence mother and father.
Oh, that's also possibility. Yeah. No, if you have only guidance counselor, the sons and daughters still sync node.
The son and daughter influences the guidance counselor.
The son and daughter influence the guidance counselor.
Yeah, yes, sir.
That's possibility. Yes. Okay, good. Yes, you can add a communication link. Yeah, from the children to the parent. That's also good. Very easy. Yes, Geraldine is correct. Okay, super. Great. So you know how to make it strongly connected, right? So now this is another example. I can just add like this. Okay. Oh, let me remove. Okay. So I can also make it two-way communication here and come back. Right. Okay. So now my question is like this. Which system is actually better? The left side or the right side? Right, Rafi?
Sir, I think on the right side,
Yes.
by the hierarchy of its tasking from the customers, it must be go to the analysis of marketing and sales up to management, and management will grow up any
Okay. This is what the common people think. Okay. Oh, the right side is better than the left side. Okay. But after you calculate the analysis, then you can start to see actually the left side is better. Okay. Later you will calculate. Okay. Okay. Because this is the story in the long time ago. Yeah. When the king, okay, get the feedback directly from the people. Or the president can get directly feedback from the people. Imagine the board represent the president, yeah, and the customer represent the people. Okay, if the king in the night they will go out and then they will get the input from the actual common people. Okay, that's actually better for the whole kingdom. And in fact, this one, if you calculate later, yeah, we can calculate using IFN anyway. We calculate later. Okay, this will rely on the reporting on the marketing and sales. Okay, and the right side, the marketing and sales, will become the strongest compared to the others. Okay, we can compute this later. Okay, so the point is this: people often mistakenly think about structure organization, something like this, right? You have the general manager, the manager, and the staff, yeah, as a tree. Okay, basically this is tree of dictatorship, you know. Okay, this is incomplete accountability and no oversight on the top position. Okay, there is no check and balance in this kind of structure organization. The correct structure organization must be IFN, must be pragmatic, irreducible network. Okay, so you need to include domination priority or the central focus of the organization. Okay, so who is this? The citizen, the customer, maybe the society, the community, the church, probably. So you need to include this in order to make irreducible structure. Okay, so if you want to create check system, you need to have strongly connected network. Remember, yeah, SIG node represent this is redundant. Source node represent dictator. You don't want that. Okay, so and then you need to have balance system, which is pragmatic. So when we say check and balance system, it's basically IFN anyway. Okay, now depends on you. You want to include the strength of the influence or not. If your influence strength is known, then you use cardinal network. If the influence strength is unknown, then you use premier network. Okay. In your IFN Excel add-ins, you just put equal n underscore premier network. You can get that. So computation is not so difficult. Okay, so using integer IFN, yeah, either cardinal or premier network, you can simulate, yeah, power domination among the friends, among the family, among the organization, company, even the country political system. Then you can search, okay, for the check and balance system, meaning that you need to add the node or probably the links of influence, and then you can check who has the most power, okay? And what will happen if you change the rules? What will happen if you change the power dynamics? You can simulate, you can predict, you can control actually based on that. I will show you in a moment, okay? Example in the family, okay? in the family, so that you will see. Okay. You create the check and balance system by creating the capacity matrix. Okay. Remember, capacity matrix represents the short-term condition of the strength, the current condition. Okay. And then if you want to get the long-term condition, okay, so equilibrium, right? So you get the premium network or cardinal network. Yeah. Remember, once you get the premium network or cardinal network, check the node flow, yeah, the sum on the right side or at the bottom. That represents the power. You can run them, you can get the relative flow, okay, of the nodes, represent the power. Yeah. And then after that, you can change the structure, the network structure, or the influence strength. And then you can compare, yeah. You have base scenario, alternative scenario, and so on. Okay. Ideally, of course, you will search until you get the optimum network structure and strength, okay, to find the best system, ideally. Yeah. At least you have a base scenario and alternative scenario. Okay, let me show you simple but nice example, okay, in the family. Okay, again, this is the family that you have. Okay, okay. Say it's very small family, only father, mother, and son and daughter. Okay, and this is redundant. Okay, we don't want that. So let's make a first strongly connected family. Okay, where the mother influenced the father influenced the daughter, and then the daughter, this is the eldest daughter probably, influenced the son, and then the son influenced the mother, and the mother influenced the daughter. And yeah, so this is already irreducible, right? Strongly connected. Yeah, from one node you can go to any others. And you look at this computation. Okay, once you put this adjacency matrix, you can get the premier network. Yeah, this is the premier network. So everything with the star here is premier network. Okay, this is the first scenario. So I put one subscript here. So FMSD represent the name. So father, mother, son, and daughter. Okay. So and then you get the sum. Oh, you see, based on the structure alone, I did not even know the strength of the influence. I can guess that the mother and the son and the daughter have equal dominant power. The father is the weakest in this family. Okay, with this now you can start to check the actual power balance within your own respective family. Nah? Okay, let's see. The nice part here is what will happen. Okay, we change the structure. Okay, say you have a yaya, a new yaya in this family, house cleaner. Okay, and of course this yaya is under the influence of the mother, but this house cleaner is quite smart, so she make a good friendship with the daughter because she knows the, okay, maybe based on the gender. Okay, so question, okay, what if there is a new house cleaner who make good friendship with the daughter and under direct influence of the mother? Okay, what will happen? Okay, the same family, but we add new node here. Okay, let's analyze. Okay, so there we calculate the second premier network. Okay, now we change. Now the H here represent the housemaid, the house cleaner. Okay, and then get the strength. Okay, oh, because of this new person in the family, the daughter now become the dominant, the most dominant, 4. Okay, the power is 4 for the daughter. This is very funny. Okay, the father is actually weakest in the family, even weaker than the yaya. Very poor father. Yeah. Okay, and the son and daughter have the mother and the son have the equal power. Yeah, 3 and 3. Interesting. Okay. So next. Okay. Let's say the father knows that he is the weakest. So then he start to learn about management. Okay, he learned management. Okay. Okay. So now he want to learn how to influence everyone in the family. Okay. So now the question is, will his power become the most dominant or not? Okay. Because we don't know the actual strength, so we use Premier Network. Yeah, Premier Network to predict the power of influence. So this is the second scenario. Okay, we add these things in the red. Can you see this? Things in the red. Huh? Okay, so the father influenced the mother, and this is already there. So then adding influence the son also. Okay, not dictatorship because this is still get influence from the other also. So let's compute. Okay. Oh, can you see the premier network showing the father's learning management can influence everybody in the family? Yes, it increased the power. Yeah, it increased the power, but it increased the power over the yaya only. Okay, so with this new structure, the mother now become dominant, huh? And the power of son and daughter are equal. Is this something nice? What do you think? Okay, you can start to analyze. Okay, something that you never think that you can analyze. Okay, so what is the relative power in this case, yeah, of this family? Because this is not one, so you can divide by the minimum. Okay, so say 3 is the minimum, right? So I can get the relative power here. Okay, so now I know, okay, that the housemate is say power 1, that the father is just 33% higher than the housemate. Okay, the mother have power of 2 compared to the housemate. Yeah, this is the relative power. Okay, is it clear? So what's the lesson? Okay, having more influence to many people does not mean that you will become dominant. Okay, because dominant power depends on the network structure and the strength of influence rather than just the number of influence. So yeah, this is where the social media make it wrong until today. They count based on the number of influence, not the structural influence. Yeah. Let's say, give another example. Let's name it family B. Okay, this is another love story. Okay, so here they have very good communication. Yeah, the mother influenced the father, and the father influenced the daughter, and vice versa, and also the daughter. What's missing here? What's missing here is actually the father and son have problem. Okay, there is no communication between father and son. And you see, so because I know the influence strength in this point, in this example, I know the influence strength. Okay, these are the influence strength. Okay, because this is influence strength, so okay, I put this as capacity matrix. Okay, it is already cardinal network, basically. Okay, so let's calculate the premiere of this. Okay, so if you calculate the premiere network, you will get this value. If you calculate the cardinal network, you will get this value. Okay. In this case, what is the meaning? The father have power 2, the son have power 2, the mother and daughter have power 3. So in these diagrams, okay, so the mother and daughter become dominant. Okay, because the father and son actually do not have communication. They need to communicate through the mother or through the daughter. So they become dominant. Okay. But if you know, because you know the actual strength of influence, okay, and you calculate that, so then you can calculate using a cardinal network, which is quite complex here. Okay. So you you will see this cardinal network have different values. Let's calculate the power of this cardinal network, yeah? So that you can see, oh, there, okay? The power is actually, the father have influence 1, okay? And then the mother is actually the strongest in this family. The daughter is 2 times, and then the son is 1.5, almost 1.6 times. Okay, compare this cardinal network with Premier. You will see Premier is rough. Okay, so this is 2, 2, 3, 3. Okay, this is rough. Okay, so roughly telling the dominant structure because Premier is based on network structure alone. It does not know the strength of influence. Okay, the cardinal network is the refined values. Okay, it knows the actual influence. So if you have the actual influence strength, use cardinal network, not the Premier. But if you don't have, use Premier. Okay, that's the main point here. Okay, let's say what will happen. Okay, if the father and the son repair their communication. Okay, so that means I have a new two links here. This is the second scenario. Okay, so this is the first scenario, C1. This is the second scenario. I added this 1, 1 here. Okay, then we compute. Yeah, so when we compute, okay, of course, Premier network becomes structurally ideal. Yeah, everybody have equal power. Full communication. Yeah, this is the actual communication should be like this. Yeah, in terms of Premier. Okay, based on structure alone, this is good. Okay, but because in reality, okay, in reality, the strength of influence is not the same for each between each person, right? In that case, this cardinal network reflects better power dynamics than that Premier network. Yeah. In this case, actually, the mother still dominant. You know, the daughter and the son. Yeah, this is 35, right? It's the second dominant, and the father still the weakest in this case. Yeah. So the change of the structure, okay, of this communication compared to scenario 1 and 2, it actually benefit the son more, right? So the son get more domination here. So if the son knows this, okay, then the son supposed to repair that communication with the father. Correct? Okay. So yeah, this is the strength of influence. Yeah, the father is still the weakest. Yeah, the mother is 2 times, and this is like 50%, yeah, almost 50% higher influence in the middle ground. So compare that to scenario 2, scenario 1. This is my scenario 1. This is the power. If you run, okay, they are the same. Okay, but if you look at the power of influence, okay, the relative power here, they are not the same. Yeah, the change in scenario, okay, actually change the power dynamics. Can you see this? And the power dynamic change. But in terms of the ranking, okay, they are the same. Yeah. So that's why if we want to get the more refined, we can do this. Yeah. So what's the lesson? Yeah, you can improve communication to increase the balance of the power. Yeah, and actually cardinal network is better than Premier. Okay, now in here he knows. Yeah, now scenario 3. Yeah, last one. Okay, in this family, the father knows that he is the weakest, right? So then he's trying to simulate this problem. Okay, he can top control. Okay, and then he can change the values. Okay, so that he will become dominant. Okay, how to make sure that he will become dominant? Okay, the minimum is 4 in here. DF and SF here should be 4. That's to be the minimum. So you can control. Is aside from understanding, you have the prediction. Now you can take control because you have the model. Okay, but on the surface, he can take control. But look at this, the meaning, rather than just take control. So on the surface, it has no problem structurally, right? It has two-way communication, as remember. But the strength of influence, the capacity matrix, is actually the problem. Okay, what will happen if he use this into 4? What's the meaning of this DF4 and SF4? Okay, so if we compute this scenario 3, okay, he will become the highest. Yeah, the father will become the highest here. Can you see? Okay, so he will become the most dominant, and the mother become the second dominant. The daughter and son have equal power. Oh, seems okay, right? Seems okay, right? It's like traditional family, isn't it? So this one, yeah, almost, and the power is almost balanced also. Seems okay, right? So, but what's the problem then? Yeah, in scenario 2, this is not good. Yeah, the mother is dominant. Yeah? But the problem is actually the meaning of this strength of DF4 and SF4. Yeah, what that mean? That meaning that children now depend more on the father than the mother. Okay, that means if you change the father to take more control, that may lead to the competition or power struggle between the mother and the father. That means they will spoil the children. Okay, that will create unhealthy competition for the power within the family. That may lead to spoil the children. So if you know all of this and you are the father of the family B, is it love, okay, for you if you don't take control of scenario 3? It's okay to be in scenario 2. You got it? So family stories is actually related to everyone, yeah, because everybody have family. So my point is you can use IFN, okay? It will show you the quantitative analysis on the numbers, okay? How much? Okay? You can understand the structure, you can predict the power dynamic, okay? And the struggle within the family, and then you can simulate, you can control if you want. Okay. Until here, any question? I think the time is up.
Sir, if I may, sir.
Yes.
Sir, on the slide 63,
60.
the DF4 and SF4, sir, as I interpreted at the adjusted matrix, sir, the daughter has more influence. The daughter influenced the father.
Yes. The father, to make it father take control, that means the daughter more influence to the father. How to do that? Okay, that means you give chance to the daughter to give influence to the father, right? The same thing, the son will have more influence to the father. That means as the father, you give chance to the daughter or the son to give more influence to you. How to do that? Dependency. Right. That's why it will lead to the power struggle. Yeah.
Thank you, sir.
Yes. So each number, you need to understand the meaning, not just putting numbers without understanding the meaning. You need to interpret. Is it clear? Yeah. So, okay. Is there any other? Okay. So with that, so we can continue this next week, okay, with more examples, and then go to the mathematical list so that you can start to analyze on your own, okay, for your project also. Give me feedback. Is this something interests you or something that I already know or something?
Yes, sir. This is very interesting. I didn't know that these kinds of things can actually be calculated.
Oh, based on just drawing only, you can calculate. Yes, of course you can.
I'm very interesting. I mean, I'm starting to think on other kinds of applications that this can be used. So, yeah.
Mhm. Yeah, so you can use this for your group projects if you want. It's pretty easy, right, to create those kind of network.
Yes, it's easy, but yeah, you have to determine the value. For example, the influences in relation to value or the
Yeah,
strength. Yeah,
the strength of it.
you are the one going to
Again, if you don't know the strength, that's okay.
yeah
Just 0 and 1 is okay.
yeah.
Go to the premier one.
Okay, the premium one. All right.
So if you don't know the value, that's okay. But if you know the value, it will be more refined. Okay. And then you ask me, what will be the value? Can I get the value? Well, because this is the ordinal value. So, well, you can do survey if you want, or you just ask question, or you just estimate. That's okay. Okay. All right. So the actual data does not really matter, you know. We don't want to get the actual precision, right? But what we want is actually how we can see the influence, and then how we will quantify this influence, and then how can predict and control the situation. Okay, I hope this is useful. Okay, more math next week. I will have one assignment for you, which is a while ago equivalent. Yeah, so I'll post it in Moodle.
All right, sir. Thank you.
All right, thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Bye.
Thank you, sir.
Bye. Good night. Good
Sir. Sir, may I have one clarification again, sir?
Yes.
Sir, regarding assignment, sir, do we have a chance, sir, na if we do miss wrong answer, could we have a chance to correct it, sir?
Oh, okay, no problem. Okay. If you have wrong answer, you have until the end of semester to correct it.
Once we submit it, sir.
Yes. I will check, then I will keep comment. You can resubmit, no problem. Okay.
Thank you, sir.
That's how we learn, isn't it? So you
Yes,
don't I don't judge you. Okay. I'm the facilitator here. Okay. I'm just a teacher to facilitate, to improve you. Okay. I don't judge. So no need to worry. Okay.
a chance to
Yes, you can always
have
improve.
good grades.
Yes. No worry. Okay. But submit it on time, and then give me chance to check. Okay. One day before the next week, say on Thursday, you submit it, and then on Friday I will check and give comments, feedback to you. Okay.
All right, sir. Thank you very much for that.
Thank you.